morning. That's right, good. So welcome to the physics department. My name is Simon Cornish. I'm the current head of the Quantum Light and Matter group in Durham. And it's an enormous pleasure for me to introduce today's speaker, Professor Charles Adams. Charles has been working with light, lasers and atoms for over 25 years. And I think it's fair to say that, like many physicists, he has an obsession with control. Okay? So in his PhD research back in Strathclyde, he developed new methods to control laser light. And in fact, the laser he developed went on to sell worldwide. And it made a lot of people very wealthy, I think it's fair to say. Fortunately for us, Charles was not one of those people. He instead pursued a career in academia, and he moved abroad to Germany and then to the United States, where he explored ways to use the light to control atoms at that stage. He moved to Durham in 1995 as a young lecturer, and over the subsequent 20 years or so, he has really been instrumental in developing the Quantum Light and Matter group here. We're now recognized as one of the leading international centers for research in this field. His current research focuses on the control, again, of single photons, where he's learning how to force the photons, the particles of light, to interact. And in 2014, he won the Institute of Physics Thomson Prize in recognition of that research. Charles also enjoys teaching optics to our undergraduates in Durham. His lectures are very well received. He enjoys optics so much that he's written a book on the subject, which is something that he might just mention once or twice during his lecture. Finally, let me comment that I met Charles down a salt mine in Poland, probably back in 2003. And actually, our meeting that day inspired me to move to Durham to pursue my research career. And I'm certain that today he will inspire you with his Christmas lecture on the mystery and mastery of photons. So please, let's welcome Charles.
So thanks very much, Simon, for that introduction. I've got a lot to live up to now, so he's really set the scene. So I'm going to begin the talk with a quote. I'm going to end the talk with a quote. And for me, these quotes capture the spirit of science, and they're also going to be my sort of Christmas message to you. So the beginning quote comes from Niels Bohr, who was a very famous physicist, father of quantum physics and the theory of atoms, the quantum theory of atoms. And he's a great physicist for quotes. He came up with many good quotes. And he said that every valuable human being must be a radical and a rebel, for what he must aim at is to make the world things better than they are. And I think that's very much the spirit in which I'm a scientist. I like to think of myself as radical and rebel. I don't like to follow the crowd. I like to do things differently. But I do that because I believe I can try and make things better in some way for people, hopefully. Okay, so this talk's going to be about light. It's going to be about the fact that light is made of photons, what we know about light. And I'm going to start with a history. So we're going to whisk through 1,000 years of history, and we're going to redo some of the most famous experiments in the history of optics that have brought us to our current understanding of how light works. So we're going to start by going back 1,000 years. And the first book of optics was written by an Arabic scholar known as Al-Hassan. He wrote a book of optics over 1,000 years ago now. And this is one of the drawings from his book, and it shows the sun reflecting off some parabolic mirrors. And the idea here is if someone's trying to invade, then you can blind them with sunlight by focusing the sunlight on the people that are trying to sort of invade your city. But the basic idea that he had understood was that light travels in straight lines. This is a quote from a Chinese philosopher around 1600. He says light is fat and shadow is thin. We use this as a quote in one of the opening chapters of our book. But I'm not sure what he meant actually. So, but maybe he meant that when it's light, then the crops grow big and fat, or the animals grow big and fat, and when the sun doesn't shine, then nothing can grow. Maybe it meant that. But maybe it also meant what we see when we see light propagating through the woods, through the trees, and you see how the light spreads out. So here you see the light is fat, and it spreads out to fill up the shadows. So that's one of the sort of phenomenon that we'll look at. So the basic idea that we had 1,000 years ago was that light travels in straight lines. So this was already known. And when Newton came along, so Newton was the sort of father of modern physics, he wrote a book in optics, 1704, and he said, light is never known to follow crooked passages nor to bend into the shadows. So slightly different to the light is fat idea, that it might sort of spread out into the shadows. And Newton did a very nice experiment, which is not so well known or not so often reproduced. And it's an experiment where we send light through the gap, the wedged gap between two knives. So Newton says in his book, so this is Newton's two-knife experiment. He said he had one knife, and then he says, I placed another knife by this so that their edges might be parallel and look towards one another, and that a beam of light might fall upon both the knives and some of it pass between their edges. So what we're going to do as our first experiment is do Newton's two-knife experiment. So I've got a laser and I've got some knives. And as my colleague always says, intense laser light, sharp knives, room full of students, what could possibly go wrong? So let's see. All right, so I'll turn on the laser first. And I'm going to switch to my webcam so that we can get this on the screen. So I've got a laser and I've got a webcam. And it's not so intense, I can put my hand in the beam here and things like that. So you can see my hand going through the... and then inside this box, I've got my sharp knives. So these are two knives, these nice Sabatier knives, and I've hammered them into this wooden block, and you see there's a kind of wedge-shaped gap. So we're going to send this is exactly what Newton did, was send, so he used sunlight, but we're going to use, so what we see is a pattern that doesn't look at all like the shadow between the two knives. So imagine the knives are getting wider at the top here and narrower at the bottom. But what we see is that the light, where the gap is very narrow, we see the light is spreading out a lot more. And we also see, well, you can see on the thing here, but not on the screen, you can see these fringes. So does anyone know what this phenomenon is called? When we send light through a very narrow gap. Any suggestions of what this is? Something you might have come across. No ideas? Yeah. Diffraction, exactly. Yeah. So what we know is that Newton was kind of wrong, right? So Newton said light travels in straight lines. It doesn't bend into the shadow. But he did this experiment, and what he saw was that light bends into the shadow. So he's not as well known for his and then if I just show the picture now that Newton drew in his book, it's exactly like what we saw on the screen here. So we've exactly reproduced what Newton saw, and you see he's drawing these sort of spreading out. Here's the wedge between the knives, and where the gap gets very thin, we see this spreading out of the light into this gap. So although Newton said that it doesn't bend into the shadow, we see that it does. And so this is at the first point where we really learned that light doesn't travel in straight lines, actually. Light can bend. And Newton does write some strange words about these particles of light traveling along curvy linear lines. But he didn't really get this idea that light was a wave. So he believed that light was made of particles, and he didn't want to abandon that, and so he couldn't quite cope with the wave description. But this was the first hint that light might not be just particles, and it might be a wave. And actually, Newton's theory of everything kind of stuck for a long time. So physics didn't advance because Newton did so much good work that everybody believed everything he said, and nobody questioned. There were no rebels. So you had to be a strong character to rebel against Newton. And it took a while before new discoveries were made in the history of light. And the next one was made by Thomas Young. Thomas Young was a doctor. He was interested in vision and sight, so he started doing a lot of experiments on light. And this is his biography, and on the biography you see he's the last man who knew everything, which clearly there was a lot more things to know that hadn't been discovered yet, so things that were discovered after him. Now, he did a similar experiment where he sent light on two holes, and now what we know is from the two-knife experiment that it's going to sort of spread out, and as it spreads out it starts to overlap. And actually if you look at the pattern, again you don't see the shadow of the two holes, you see this kind of pattern here. And over here my assistant Charles has got a modern variant of this experiment. So again we've got a red laser and it's hitting a double slit, very small slit, and then here we have a detector, and the detector is very similar to the kind of detectors you use in your camera or in your phone, but now the detectors are so sensitive that they can really count photons. So if you look at what happens in the screen here, you see these little blobs, these little squares. So this is the pixels of the camera, and we're actually counting photons as they come through this. So essentially this is doing Young's experiment now, but in a modern way, where we can do it at very, very weak light levels and detect and count photons. And what we're going to do is leave this running for a long time and see how the pattern emerges, and see if we get a similar type of pattern to Young was predicting. Now this was a very significant point in the history of optics, and it was the first, it's often, we teach this as the first experiment that really proved that light was a wave because of this interference phenomena. So basically the light can go through one or other of these holes, and then the two paths can interfere, and these interference gives us fringes of light and dark. So these are known as interference fringes, so the maximum and then dark and then light again. And if you do this with white light, you also see that the different colors spread out by different amounts. And because it's so significant, I chose this as the picture that for the poster for this year's Christmas lecture. And this is pictures also in the book, by the way, if you're interested in reading more about that. So around 1900 came along the idea, Max Planck came and said that light was made of quanta. So that light needed to be quantized, because the theory didn't kind of make sense unless we said light comes in little bundles of energy, these quanta of energy. And so now we have this sort of two views, that we have both this wave view and this particle view. So we have these quanta of energy, these photons that are going through one or other slit and then interfering. And the question that sort of arose was, well, does the experiment still work if we do it with very feeble light? And the first person to ask this question was a physicist called G.I. Taylor. And he set up an experiment in his garden where he basically did this Young's double slit experiment like we're doing with very, very weak light and photographic film. And he just let it run for months in order to accumulate the statistics and get a picture of the interference pattern. And what we find is, like we're finding over there, is that the pattern builds up photon by photon in the same way. So this photon picture, that the fact that it doesn't make a difference. So basically the light is behaving as both wave and particle. And that's the way we have to think about it. There's this wave-particle duality, which we'll come back to throughout the talk. But before we get to that, there's another mystery about light. So going back to the 19th century, there was something else. There was another strange story that became a bit of a mystery. And there was a happenstance. Something strange was discovered. So this William Byrd Harper was a doctor in Bristol. So like Young, another doctor, doing various sort of experiments, trying to understand illness and people. And but the story with Harper involved a dog. So here's a dog. Mosquitoes. So a dog plus a mosquito. That gives you malaria. So the dog had malaria. And they were trying to understand malaria. So they treated, at that time, they treated malaria with something called quinine. So you may have heard of quinine. So if you get malaria, you get quinine tablets that helps you with your malaria. So the dog had been fed quinine. And then in the laboratory of Harper, the assistant added iodine to the urine of the dog. I'm not showing you a picture of the urine. I thought it's nice to see the dog. And something really strange happened when they mixed this urine and this iodine together. They got these crystals. So they got these strange crystals. And these crystals basically changed the way they appeared depending on their direction and angle. And sometimes they were different colors, so they'd change color. They were very odd behaviors. And these crystals, now they're known as herapathite, after Herapath. And their chemical name is iodoquinine sulfate, because it was quinine from the dog urine, and then the sulfite and the iodine all formed this particular chemical. So this was a happenstance discovery. Now, what's interesting is the way these crystals affect light. And I've got some of these crystals now, in a different form. So if I put the light on, and this is something you may be familiar with, this is a sheet of plastic, but inside this plastic is this herapathite, lots of small bits of it. So basically what you grind up your herapathite, and then you put it in solution, and then you absorb it into this stuff. And this is a polarizer. So what the herapathite does is it only lets light with a particular polarization. So not only is light a wave, but it's also got this direction called a polarization. And it can have two directions. So we can say the electric field in light can either be polarized, say, vertical, or it can be polarized horizontal. So this wave is either going like this, or it's going like that. So these are these two polarization states. And let's say this first polarizer only lets through light that's going like this. So only photons that are going like this get through this one. And then I'm going to set my second one so that only photons that go like this can get through. So if these ones get through the first one and I don't let them through the second one, then I'll see that nothing gets through. So you see, as you rotate these and you have crossed polarizers, then nothing can get through. So now we've blocked all the photons. So the vertical ones are blocked by the first one, the horizontal ones, I think I said it the other way around, but let's say the vertical ones are blocked by the first one and the horizontal ones are blocked by the second one, and nothing gets through. But now something slightly strange happens if I take a third one of these. So remember, this sort of blocks either one polarization or the other, and then nothing gets through. But if I take this and put it in the gap, then you see stuff starts going through again. So I'll just put that in the middle there. Suddenly the photons are going through again. So that's a bit odd, right, from this idea that I said, oh, these polarizers remove light, so that some remove this polarization, some remove that polarization, and I put in something else that removes more light, but now I get more through again. So we could say this is a bit of a mystery, so something that we don't understand. But if I put other things in this gap here, I get even more interesting effects. So if I just take a ruler and put it between these polarizers, and I get all sorts of lovely colors. So what's happening here is not that I'm removing light, but I'm changing it. So something like this ruler must be changing the polarization. It's not just removing. So this thing doesn't just remove light, it changes the polarization of light. And similarly, this changes the polarization of light. So the next stage in this story was this idea that you could change the polarization. If we go back to the slides now. So the next stage was how this was exploited in the history for useful purposes. So there's a very famous experiment that was done by Biot, Jean-Baptiste Biot, who was a French person, in around 1815. And this is a picture of him as an old man. I like the picture because he looks like one of these Dickensian characters out of Dickens. But when he did the experiment, he didn't look like that. He doesn't look like he's up to an experiment anymore. But anyway, this experiment he did was to send light through sugar solution. So it turns out that sugar has a very strange effect on light. So we talked about light having this sort of direction, this polarization, so it goes up and down. Now sugar is a chiral molecule, and these chiral molecules can twist the polarization direction of the sugar. So what we're going to do is, as a next experiment, is to do Biot's experiment using a sugar solution. And the sugar solution I've got, so you can buy, this is corn syrup. So this is a very, it's basically a syrup, but it's like any kind of syrup. So it's basically sugar, very concentrated sugar solution. You can see it's very viscous. So the Americans use this to make pecan pie. So it's hard to get here, but in America it's used a lot in cooking because they have a very sweet tooth. So what we do is fill up a tube with this sugar solution, and then send a laser beam through it. I'm going to move this out of the way so hopefully the people over there can also see. And then I'm going to put this around it just to cover up some of the scattered light. And then I'll try and get a picture of this with so my webcam's playing up. But let's see what it looks like on the webcam. Okay, yeah, so that's reasonably good actually. We can just about see. So what you see now, either if you're close to the front, you can see it directly, or if you're further at the back, you can see these. So that the laser beam comes in and you see these bands of light and dark. And if you're at the front, you might be able to see that in the dark regions it looks a little bit orange. So what happens here is that as the light propagates through, the plane of polarization is changing. And when the polarization is vertical, then the sugar molecules can scatter the light and you see them. So if the polarization is like this, you see it. But when the polarization rotates like this, and the electrons are oscillating like that, they can't emit any light in that direction. So then you don't see anything. Actually, they're emitting the light in this way. So this is called the dipolar radiation pattern, that this scattering follows this pattern. So basically, you only scatter light. So if I'm polarized like this, I can scatter that way, but not this way. And if I'm polarized like this, I can scatter that way, but not this way. So if we looked from above, we'd see the pattern a bit out of phase. So what's happening as the light propagates through there, it's twisting the polarization as it propagates. And just to show that I can control this, on the input we've got a piece of quartz, and the quartz also rotates the polarization. So by rotating the input polarization, I can twist this twist through the sugar solution. So if I now rotate this, and what's hard is to do this without misaligning the laser beam. So I don't know if you can see that moving through the... I'll just turn down the gain a bit, I think. Oh, that's the wrong one. Yeah, so I think there you can sort of see these bands of... And then if I rotate this, you see these guys moving through the solution. So basically I'm changing the polarization and twisting it. So I'm twisting the twist, and it looks like a corkscrew. And then if I go the other way, you see it moves back in the opposite direction, and similarly back and forth. So we teach this sugar rotation in our second year laboratory here because we think it's a very nice demonstration of a lot of the properties of the polarization of light and how this polarized light propagates through a medium. All right, so why was this important? Well, it was very important in the history, especially for French people. So the French, like everybody else, liked their sugar. But their sugar supply was a bit volatile because sugar comes from hot places in the Caribbean, but sometimes there were wars and embargoes, and the British kept sinking all their ships. So the sugar supply was a little bit volatile, but people loved sugar, so they'd get especially the French, they would get very upset and go out onto the streets and cause havoc. And so Napoleon decided that rather than trying to import all the sugar, maybe they could grow sugar. So rather than having sugar cane, they could grow sugar beet in France. And so they started growing the sugar beet. But then people said, oh, no, it's not good sugar. It's not as good as the sugar cane. And it was Biot that did this experiment that showed that the purity, the sugar purity of this sugar beet sugar was as good as the sugar cane. Of course, people are not even convinced by the scientific evidence, even then. But what it did become very important for is that when people were making sugar in foreign countries and trying to add bad things to it, like dust, and claim it was pure sugar, then you could detect the purity of the sugar. So it became a scientific way and was one of the first sort of food science where we actually used lasers, or not lasers, they weren't using lasers, when they used light to detect whether something is really pure, which is an important question. Okay, so this was a very important experiment. I showed you, maybe the people at the front could see that in the gaps the light was orange, so there's this orange glow to the light. Now it's misaligned itself. And if I do the experiment with blue light, which is this picture here, actually you see bands of blue and green. So in the regions where you don't see scattering, you see green light. And that's another interesting phenomenon when light propagates through a medium, which is called fluorescence. So if I send light through a medium, I don't always get out the same color. And this is how lasers work, actually, that I put in one color, and that creates some electronic excitations. And then when those excitations decay, they can emit a different color, which is usually a longer wavelength. And so here, when you put in blue, you get out some green light as well. And if we put in green, we get out some orange light. And this is one of the ways that we use to make lasers. Okay, so that's the second mystery about polarization. But polarization led to another important discovery, which was made by Faraday in 1864. So this is Faraday here. Now Faraday, so I always say that I have many favorite physicists, but my favorite physicist of all is Faraday. So Faraday came from a very humble background. His father, actually from the north of England in the Pennines, his father was a blacksmith, and then they moved to London. And Faraday was sort of self-taught, but he was a very curious experimentalist. And he really made the groundwork for the modern world. So it was Faraday's experiments that showed us how to make electricity, how to make generators, dynamos, all these things. But he did the most important experiment in the history of light in the sense that he showed that light had something to do with electricity and magnetism. So everything I've talked to you so far, like Young's experiment, the sugar rotation, nobody realized that light was an electromagnetic field. And nobody made the connection that there was anything to do with magnetism and electricity. And it was Faraday's experiments that unified all these fields together. So they said optics, light, electricity, and magnetism were all related phenomenon. So how did he do that? So Faraday looked at the propagation of light through a medium, like we've done with this sugar solution. But he looked at propagation through just an ordinary piece of glass. And everyone thinks this picture here is Faraday with a cigar, maybe celebrating his great experiment. But no, it's Faraday with a piece of glass. So it looks like a fairly brown, horrible bit of glass, but I think that's because it's an old picture. So the next experiment I'd like to do is to repeat Faraday's experiment. And what Faraday did was he took this ordinary piece of glass, and then he put it inside a strong magnet, and he showed the magnetic field changed what happened to the light as it propagated through the glass. And that was the first demonstration that light had something to do with magnetism. Now this is the experiment that makes me nervous, and I have to concentrate at this point during the talk, because we need a very strong magnetic field. And the strong magnetic fields are very dangerous. So if you have a big magnet, then anyone with any metal stuff comes flying towards you. Or any pieces of metal in the room can come flying towards us. And I know this because I experienced it in a very bad way once when I was setting up these demonstrations with a strong magnet. I was walking through the department, and an unfortunate person had just locked their office and were just with their keys, and their keys came flying over towards me, and they rushed over to try and retrieve their keys, and then they had some watch on that also got stuck to my magnet. So it was almost a great disaster. So we have the great potential for a disaster when I get out these strong magnets, not least because I've got sharp knives here. So the first thing I need to do is go and put the sharp knives a long way away. I usually say I'll put them near my assistant sharp, but I'll put them under the table here. So we don't want the sharp knives flying across the room and sticking on the magnet. So the magnet I have in that, so this is now my magnet transporter. So it's the paper disposal bin, and I put in padded envelopes so I can't get stuck to anyone in the corridor. I should turn off this laser here so I don't blind myself as well. All right, so inside here, it's this laser that's blinding me. So here's my strong magnets. So basically we've got two magnets back to back so that in the gap we get a very strong magnetic field. And then inside there we're going to put this piece of glass. So this is my cigar of glass, like Faraday's cigar. So the first thing I want to show you is just that this glass is very so I'm going to do this demonstration for the sort of people over there, and then I'll do it for the people over there. So don't worry that you can't see it initially. But the first thing I want to show you is just that this glass. So I'm just going to put the glass on here and show you that there's nothing, when I send light through here, there's nothing special about it. Okay, so I need this and I need this. I'm not going to do it on the, So we're going to send some light through this piece of glass, and some light will come through on my screen here. And then if I put in my polarizer, I can basically just attenuate the light. So this is just the cross-polarizer effect that I showed you towards the beginning of the lecture, that I block out so that I've got a polarizer on the front of my torch, and when they're orthogonal to one another, at right angles to one another, then no light can get through. So basically the glass just behaves a bit like air. So it's not doing anything special. But now if we put the glass inside the magnet, something different happens. So there's only a small hole through the magnet, so it's a bit hard to see. But I'll first do it in this direction, and then we'll do it in the other direction. Okay, so now you see there's a white spot. Hopefully the people over there can see. And then when I put it just doesn't, I put the polarizer in, and now you can see this spot. Maybe we should put the lights down a bit further. Put the lights, just do the lights off. Off. Okay, so there's this there's my light getting through here. And you can see what I can do with changing the polarizers. I always get some light through now, but the color of the light changes. So what's happening now as it propagates through this piece of glass, inside the magnetic field, is all the different colors are rotating by different amounts inside the glass, but by the effect of the magnetic field. And so what we see propagating is the color that's aligned with my output polarizer. And as I rotate that, I can change the color. So let me now do this. So if I do this experiment for this side of the room as well. So again, there's the white dot. And then if I take my polarizer here and I rotate it, you see the color changes. So I can get, so here it's almost green, and it goes to red, purple, deep purple, and then a nice blue, and so on back through green. So I can get every color out. So this is Faraday. This experiment is known as the Faraday effect, and it was really the first experiment that showed us that magnetic fields can have an effect on light. And consequently, the first experiment to show us that light is an electromagnetic wave. Now I'm going to put the magnet away again, because I don't want anything. Then put it back under here so that it's so hopefully no mishaps happen. Okay. So I have a random picture of Gordon Gekko from this movie Wall Street here, because I usually like to, at this stage, tell the story about how important history. People can only make money because there are physicists that invent things that people can make money on. So these people that trade and make money on the backs of other people, to me, are less important. And there's a sad story about Faraday used to be on the 20-pound note, and now we got rid of Faraday, and now we replaced him with Adam Smith, who's an economist. And so I think that that was a part of the decline of Britain. And we need to go back to putting physicists on the money. Faraday was a very humble person, but I think this is a very wise comment. A man who is certain he is right is almost certain to be wrong. Maybe some of our politicians should learn that. Gordon Gekko said he didn't have any friends. He had a lot of money but no friends. He said, if you need a friend, get a dog. So you can make your own conclusions about whether you want to be a financier or a physicist. That was a political slide. All right, so Faraday showed us that light had something to do with magnetism. And the person that put that into equations was James Clerk Maxwell. Here he is with a dog. He had a dog and a partner. And he wrote down these equations of electromagnetic force. So you can see now the word, so he's writing down equations that describe light, but the word electricity now appears, or electromotive. And so Maxwell was the person that basically coded the experiments of Faraday in a mathematical language. And for us in the northeast of England, there's a nice connection with the history of Maxwell's equations. Because Maxwell wrote down, you see, these are the original Maxwell equations, and there was 22 of them. They were horrendous, and we never study those now. The equations we study were actually written down first by somebody called Oliver Heaviside. And Heaviside was working in Newcastle. So he worked for a company in Newcastle, but every Saturday he used to go to the library of the Literary and Philosophical Society in Newcastle, which is still there. You can join this and go and look at the books. And one day the book of Maxwell turned up with these equations in it, and Heaviside was very intrigued by this, and he decided to give up his job and try and understand this electromagnetic wave theory. And he came up with a completely new mathematics, which was called vector calculus. And he rewrote these 22 equations of Maxwell as just 4 equations. And these are the equations that we now know of as Maxwell equations. So they should really be called the Maxwell-Heaviside equations. And there's a nice connection with the northeast of England, because this is where these ideas began. So what we know now is that light is a wave. There's also particles, it's photons. So we've got this light is a wave, and it's an electromagnetic wave, and it's this polarized wave. And the wavelength determines things like color. So we've seen different colors emerging from our crystal, different colors inside the sugar solution, and these colors are represented by the wavelength of light. And we now have this electromagnetic spectrum, and this brings us sort of almost up to date with our current understanding of light. Except that we still need to go back and say, but we know that light is made of particles, photons, these quanta, because just like we showed in this demonstration at the beginning, over here, we can count these photons, and you can see now the picture's sort of completely saturating. I don't know if we got up to, I think we've got to maximum counts. So it's not going to, I don't know what it's going to do if I just take this off now, but I think it's, oh, I don't know what it's doing now, but still going up. But I think it's saturating the camera now. But you can start to see that we built up this picture photon by photon, which is what Feynman basically said would happen, that we know that light's made of particles because we can take a sensitive detector that makes clicks or makes little squares on our computer screen when the light shines on it. And if we make the light more intense, the clicks are the same, but we just get more of them. So as we increase the intensity of light, we just get more photons. But each photon has the same amount of energy. So that's the photon idea. Now what about if we go back to our initial experiment? How do we think of that in terms of this particle picture? So our two-knife experiment, which we said was a phenomenon of diffraction, that when we squeeze the light, so when the when we really squeeze the light, then it spreads out more. So in the Newton's two-knife experiment, when the wedge was narrow, we saw that the light spread out. And when the gap was large, it doesn't spread out. So there's some minimum distance here where the two effects are sort of minimized. Now we can explain this in modern terms, in terms of wave-particle duality, in terms of Heisenberg's uncertainty relationship. So if we have this wave-particle picture, and we think of diffraction of photons, then we can, as we squeeze something more in position, so we make this delta x here very small, so that's making something small in position, then we have to have a bigger spread in the momentum. So this thing delta p here is large. And the spread in momentum means that things are spreading out with angle. So as we squeeze something in space, then it spreads out more subsequently. So because these two things multiplied together have to be greater than some amount, known as Heisenberg's uncertainty relationship, we can exactly explain Newton's two-knife experiment in these terms. So in some ways, it's a very nice, if we do this experiment with single photons, it's a very nice demonstration of the Heisenberg uncertainty relationship, which is our current sort of modern theory of wave-particle duality. But there's still odd things, there are still mysteries, so not everything is really answered even at this point. So we've got this wave-particle duality, and we can ask the photons, you know, are you a particle or are you a wave? And see what they say. So we can do an experiment that tests for the wave properties, like interference, or we can do an experiment that tests for a particle property, like where is the particle, what path has the particle followed. And we can do a variation on Young's experiment, where we can send in some light, and then we split it on, say, a piece of glass here. So we split the light in two. So some part of the light goes this way, some part of the light goes this way. So let's say some photons go this way, some photons go that way, and then they come back and interfere. Now the question is, do the photons go both ways? Do they choose to go just this way or that way, or does each photon go along both paths at the same time? Now to get interference, we have to say that the photons have to travel along both paths simultaneously. So a photon is kind of split, if you like, at this glass plate and goes on both paths, and then they recombine, and then we get some interference fringes. So this is kind of the wave aspect. So we ask the photon here, if we see interference, we say, yes, it's a wave. So we ask the photon, are you a wave? And we see the interference fringes, and it says, yes, it's a wave, because we can only get this interference pattern if it's a wave. But now what we can do is use this polarization trick so that we know which path the photons followed. So we can now change the polarization in one path. So if I put in here one of these polarizing elements that switches the polarization. So if I went in here, say, with vertical polarization, and this switched to horizontal, then when these two paths recombine, I get a vertical component from this path and a horizontal component from this path. And now I can tell which path the photon has followed. And if you do this experiment, what you find is that these interference fringes go. Because here we've asked the wave question. We said, are you a wave? By rotating, we asked the particle question, said, are you a particle? And now there's no wave phenomenon. There's no interference. It says, yes, I'm a particle. So we asked the wave question, are you a wave? It says, yes, I'm a wave. Are you a particle? Yes, I'm a particle. But how can it be both things at the same time? So an interesting thing that happened in the last sort of 50 years or so, or even the last 10 years, was the idea that maybe we should look at this more deeply and explore this. This is a bit odd. So the idea for an experiment came from someone called John Wheeler, because he said, in any field, find the strangest thing and then explore it. So in some sense, in quantum mechanics, the strangest thing is this wave-particle duality. How can photons be both wave and particle at the same time? He said, let's do this interference experiment, but now let's try and cheat the photon. Let's try and trick the photon. We're going to sort of not tell it whether we're going to measure. We're not going to say, oh, we're going to measure whether you're a particle or a wave. We won't ask the question till later. So when does the photon decide? Well, it has to decide which way it's going to go at this piece of glass here. So the decision is made here, whether it's a particle and it goes one way or the other, or it goes both ways and then it's behaving like a wave. So it can't do both. So this experiment was actually tested not so long ago, so about 10 years ago, somebody did the experiment in France. And so they sent in photons, single photons, and they had one of these pieces of glass that split it into two paths. And then in order for it to be inside the thing, so they needed very long paths because light travels very fast. So you see they had 48-meter long paths, so enormous, great thing. And then the decision about whether we're going to measure this wave aspect, whether we're going to measure polarization or interference, is taken later in this device. And then they had a switch here, an electronically controlled switch, where they could switch between asking the wave question and the particle question. So they were tricking the photon, and it's called delayed choice, because we don't decide what thing we're going to measure until after the photon had to make its decision about which path it was going to follow. Now the thing that's interesting about this result is you can't trick the photon, right? So still when it comes out in the end, if you ask the wave question, so once you analyze all your data, you say if you ask the wave question, it gives you yes, it still says yes, I'm a wave. If you answer and you get these interference fringes, whereas if you ask the particle question, it says yes, I'm a particle, and you see no interference, the interference is gone. So we can't trick the photons, it's something intrinsic. This wave-particle duality is really intrinsic to these quantum objects, which is really something that we're still struggling and trying to understand. So my best way of understanding this, so the fact that something can be wave or particle, but we can only see one or other of those things at any one time, is known as complementarity in physics. So it's a very interesting phenomenon that we still struggle to understand. So Henrik Hertz said maybe one image is suitable for one purpose, another for another. That doesn't really get you very far. This is not something we can understand. And I find the most useful way to visualize this is with these drawings of Escher. Because here, if you look at Escher's drawings, again you ask the question, do I see a vase? And everyone would say, yes, I see a vase. If you ask the question, do you see two faces? Then everyone would say, yeah, I see two faces. But you can't see them both at the same time. It's very hard to look and say, yeah, I'm seeing both, because you focus on one property or the other. And similarly with this picture of the horses, you say, yes, I see white horses. If I look for white horses, I see white horses. If I look for black horses, I see white. So this kind of a visualization of this complementarity of this wave-particle duality. Now, if you're feeling on uncertain ground at this point and saying, well, I'm still struggling to understand this quantum weirdness, what's going on, then you're in good company, because Einstein, quite late on in his life, said, I spent almost my whole life trying to understand what a photon is. So basically these are still hard questions for all of us. So we're very familiar with photons, but we can't completely grasp some aspect of this hidden reality that we can't really cope with. And this is Roy Glauber, who won the Nobel Prize for the quantum theory of light. So this is the most advanced current theory of light, quantum theory of light. He won the Nobel Prize in 2005. He's still alive, so I've had the pleasure of meeting him. And he has a very famous quote about photons, which sort of says what it's possible to say, which is, I don't know anything about photons, but I know one when I see one, which is a bit of a kind of joke on how little we can say. So there are still mysteries, still things that we need to solve, and so we're hoping that maybe some of you might join this exploration and solve some of these unsolved problems in quantum physics. Now the talk was called I think we've got the lights out, haven't we? Yeah. So the talk was called The Mystery and Mastery of Photons, and so far I've mainly been talking about mysteries. But a lot of my research has been on the mastery. Gaining control, as Simon said at the beginning in the introduction, that we're trying to control photons and master them. So what kind of things are we doing? What are we aiming to do in the future? So let's have a look. Okay, that's mastery of photons, right? And the cool thing about this is when you turn it on and off, it makes a really nice noise. Okay, so let's think about what this thing is. Right, so the idea is this is a solid of light. So it's a solid of light, so when I sort of bash it on my arm like this, it hurts. But is that possible? Can we make solids of light? And the answer is, well, we don't really know how to do that. So they can do it in the movies, but we can't do it in real life. And the reason why we can't do it is because photons do not interact. So if I take beams of light, two people have beams of light, they don't like collide with one another like this. They just pass through one another. So even with the laser pointer, I can just walk straight through the laser pointer, or I can, so I've got my laser pointer here, and I can put my hand straight through it. It interacts with my hand, but I can't deflect it. Or if I have two beams of light, then they don't interact with one another. So there's very weak interactions between photons. And just to see how weak they are, you can look at the fundamental theory of light, the current theory of light, and you can get what's called a cross-section, which gives a kind of probability for light, two photons to collide. And it's an extremely small number. And what that number means is if I took the sun, our sun, which has got a lot of photons, and I focus them down with a lens to a size that's of order of the wavelength, and I took another sun, and I focus that down such that these two focused sunbeams would overlap here, then I would only get one photon collision about every billion years. So it basically never happens. Even with the most intense light sources I can get, I don't see these collisions happening. So this lightsaber thing is just not going to happen. But is there some way that we can engineer a situation where this becomes much larger? And that's one of the things that I've been working on here in Durham. So here in Durham we do, you might call it experimental particle physics, where our particle that we're working on, so these are all our fundamental constituents of matter, we're working with photons. So this is one of the fundamental constituents of matter, and the question that we're asking is, can we make the photons interact in a way like we see in that lightsaber, so that we can bind photons together to make solids of light, for example. And our experiments are done just down the corridor here. So many of you have done the tour of the laboratories, and you'll have seen there is doors and there's things going on behind those doors. And this is one of the doors, and our laboratory is behind that door. And behind there is this is our apparatus, and this is a vacuum chamber. So inside here we basically make an interesting optical medium based on atoms. So we use rubidium atoms, we make them very cold. And these atoms then construct a very strange medium. And inside that medium, we can make photons interact. So this shows a picture of an experiment that we did last year, where we send some photons through one medium here and another medium some distance apart. And now the photons essentially collide. So they talk to one another. If there's a photon here, then it bounces off the other one. So these are photon-photon collisions. And actually, if you work out, basically we've gained, in this probability to photons interact, we've gained 60 orders of magnitude. So where we said for sunlight it was going to be once in a billion years, we can make this now happen basically every second. So we can have these photon collisions happening all the time. And this is the data, which I don't need to go into. But the interesting question was, how do we do that? How do we suddenly make photons interact? Well, we have to map the photons into something that does interact strongly. So I talked a bit about energy levels. So when light goes into matter, then it excites the electron. And now we can have an excited atom. And the atoms have these discrete energy levels. So if I tune my laser, my input photons, to have just the right amount of energy, this will excite the atom. And now the trick that we make is to add another laser that makes this atom really excited. So this extra laser that we add doesn't just create one excitation, it takes us right to almost the limit where the electron leaves the atom. So now we get this giant atom where the electron is in an orbit that's enormous. So actually these atoms are about 1,000 times bigger than the usual atoms. So we kind of blow up these atoms like into enormous balloons, and this shows in time what happens, that the photon comes in, then we change this, the light slows down, and it creates this enormous atom, which is this blue thing here, and then goes out again. And these enormous atoms can talk to one another very strongly, because this electron is now in this enormous orbit. And basically, if there's another one nearby that's doing a similar thing with an electron in an enormous orbit, then they feel one another, because the electrons feel one another. So in that way, we can create these strong photon-photon interactions. So we're sort of a step towards making this lightsaber. And the first time I gave this talk, someone asked the question, is that all you want to do, make a lightsaber? Is that why you're doing this? And actually, it's not. It's not the reason. So we do it for various reasons. One of the reasons is just because you can ask the question and we want to know the answer. So there's the curiosity reason. But there's also the applications reason. So one of the things you'd like to do is maybe build a different type of computer where you replace electrons with photons. So you do everything with light. So light is really convenient to work with. We can send it down optical fibers. Now all your broadband is done with optical fiber broadband. And actually we'd like to do all the processing, everything with light, and never really have to go back to electronics. So we'd replace all the electronics with photonics. But in order to do that, you need photons that interact strongly. So you can build a device now using these strongly interacting photons where if there's another photon coming in, then the photons are modified by one another. And that way you can basically replace all our electronics by photonics. Right, I'm pretty much at the end now, and I'm going to finish up with my end quote. So just to remind you, at the beginning we said the spirit of science was to be radical and a rebel in order that we can make the world better. And a quote that I like a lot is from Marcus Garvey, who gave a speech just before the First World War. And part of that speech was used in a Bob Marley song known as Redemption Song, which you might know. So it's a very famous line. But in this speech he says, "The man who is not able to develop and use his mind is bound to be the slave of the other man." So my parting message to you is, use your mind, be radical, be a rebel, and make a better world. Thank you.
Thank you very much, Charles. I'm sure Charles will be happy to answer some questions if there are any. Yes?
What made you want to be a physicist?
That's an interesting question, but I think it was this idea that I think it was wanting to change the world, really. I mean, it's getting very deep, but you know, there's an aspect that you want to live forever, right? So I don't know if I'm going to achieve that, but you know, if you can do something and be remembered for that, and people think you've done something good, then that's obviously very rewarding in life.
What do you do on a day-to-day basis?
Yeah, that's interesting. So there's a big change from when I was sort of younger and I used to work in the laboratory on these experiments, and then I would align laser beams, you know, so I would be, and to the situation that I'm in now, where basically I have to direct others doing the fun stuff. So Charles works in my laboratory where I showed you the door, and what we do is we meet every week. Sometimes I get to talk to them in the lab, and the other times they come and meet and we look at the results and we plan what we're going to do in the experiment. So unfortunately I'm not at the coalface, so to speak, anymore, but I sort of direct the research. So I spend a lot of time thinking about what experiments we should do, what we should do next. I also do quite a bit of teaching. So a lot of the demos I've shown you today, last week I did them for our second year undergraduates, so that takes up quite a lot of our time during term time. So we're sort of 50-50 educators and 50% sort of researchers. And actually, because this is the way life is, we also have to fill in a lot of forms, which is the bit that I like least.
If not, I hope Charles has inspired one or two of you to follow his lead and be a radical and become a rebel. But let's thank him one last time for a great job.